Just pin it to your collar or something. That should work, or maybe a little higher.
Hello, everyone. This talk is going to be modular quantitative monitoring. This is me, and these are my collaborators. And you should understand within the first few minutes if you don't understand the title right now. OK, so let me begin by going over two application domains that we're very interested in. So the first application domain is arrhythmia detection. So in this, people have these heart devices that are implanted into the heart. And the goal is to detect arrhythmias, which are when the heart goes too fast or too slow, or unstable rhythm. And these arrhythmias can be potentially fatal. So what happens with these devices is they're implanted into your heart, and they begin by detecting a heart signal, which is like an electrical signal of the heart. And that looks something like this. And then it has some like peaks at certain times. So this electrical signal is converted into a Boolean signal. The Boolean signal is then fed into a arrhythmia detection algorithm, which reads in the Boolean signal and decides is there an arrhythmia or not. And then if there is, it delivers a shock to the patient, potentially saving their life. So in this domain, what I want to highlight is about this detection algorithm is that it's a streaming algorithm. So what that means is that it processes this Boolean signal one item at a time. And it has to deliver the shock or not every item that it processes. It has to use a constant amount of time to process each element. And it has to use a constant amount of space independent of the input stream because it's a small device that's implanted. And you would like to specify this detection algorithm at a higher level rather than writing this low-level code. And you'd like to get a guarantee on these costs. So you'd like to be guaranteed a certain constant time per element and a certain constant space at compile time when you write the specification. The second application that we're interested in is runtime monitoring. So this is a very old field where basically you want to not verify a system, but check a system's properties while it's online rather than offline. So you begin with some kind of online system, such as a compiled program. You instrument the system with some code which basically emits some kind of output, like some diagnostic events. Certain events are occurring, maybe certain values in the program. And then you feed in this diagnostic event stream to a monitor, which is created from a specification that you write. And the monitor either reports a violation or it does nothing. So once again, in the runtime monitoring world, it's very important that this be a streaming algorithm. And so you're interested in processing the events as they arrive, item by item. You want to use a constant amount of time per element, and you want to use a constant amount of space. So again, we want a high-level language to express the specification, but we also need it to compile down into a low-level monitor with these timing guarantees. So if you are working in either of these domains, there are a number of languages that are available to you, declarative specification languages. And I put some of them on the slide here. Basically, that allow you to go from a high-level query to a monitor. And they differ in a number of ways. And in particular, they may not be adequate in a number of ways. So one thing you can look at is the expressiveness of these languages. Some languages do not allow you to express quantitative properties. If you're interested in monitoring quantitative properties, like for example, in the heart example, they may differ in the succinctness of the compiled code or the evaluation costs of the compiled code, which are related usually. Usually, if your code is more succinct, it's in this setting, it's also more efficient to evaluate. And then finally, they may not offer modularity of computation, of compilation, which I'll describe what I mean by that on the next slide. So what do I mean by modular compilation, and what do I mean by modular quantitative monitoring in the title? So the best way to understand modular compilation is to go back to regular expression evaluation from your undergraduate computer science class. So when we evaluate compile regular expressions, one effective way is to use NFAs. And when you use NFAs, if you have an expression like R concatenate S, and you want to get a compiled code for matching strings that match that regular expression, you can use a compiled monitor for R and a compiled monitor for S. So an NFA for R and an NFA for S. And you just stick them next to each other, and then you add one epsilon transition. So basically, to get a compiler for a compiled code for the full expression, you just compile the sub-expressions and then combine them with some single epsilon transition in this case. So what is the benefit of this? Well, you get a compilation essentially for free. It's not really for free, but what I mean by that is that if you have constructions for each operation in your language, then your compiler is free. You also get an extensible language, so you can, if later you want to add more constructs to your language, you can add them as long as you have a corresponding construction on NFAs. And finally, you get this key property that we're interested in, which is this guaranteed cost of evaluation. So you can find the cost of evaluation of the regular expression just by calculating statically the size of the NFA that will result from compiling it. So our main contribution is to provide a similar model as NFAs for general purpose streaming. So what we propose is this general purpose intermediate representation that you could use for general data stream monitoring applications like the ones like runtime monitoring and like real-time decision making. So you could take any of these languages that already exist, and as far as any of these different languages, the constructs from that language can be compiled down to data transducers. And using this data transducer intermediate representation, you can then get the compiled code that runs on the actual input stream. So what's the advantage of this? Why are we proposing another model when there are a lot of models already? Well, the main reasons are the four here. So compared to the existing languages and existing models, we have greater expressiveness. We allow this modular compilation, or we enable this modular compilation. We have an efficient streaming evaluation algorithm for DTs, for data transducers, which basically implies a guaranteed cost on the compiled code. And finally, we've proven that our model is maximally succinct in a certain sense. But concretely, what it means is, again, that the cost of evaluation, because of this efficient streaming evaluation, is known statically, and it's very efficient. And in fact, even if you look just at the modular compilation alone, the set of composition operations that we're able to support on data transducers is, we don't know of any model that can support them. So that was our main goal in this model, was supporting these specific composition operations. And so to support those, we defined this new language, QRE-Past, and we combined previous quantitative constructs and constructs from some of these other languages like temporal logic constructs, and we showed that using data transducer operations, you can compile this combined language for free into efficient monitors. Okay, that's the high-level overview. Let me just provide a brief outline of what I'll talk about for the rest of the talk. So I'll describe the model and just so you get an idea of what the actual model we're proposing is, because it's, I think, simple enough to understand. It's just two things, quantitative states and transitions, and I have to tell you what those are. I will describe a little bit about, very briefly, the composition operations that we support and how we compile those. Then I'll discuss expressiveness of our model, in particular expressiveness of data transducers versus general streaming computations. So You might wonder why not just use general streaming computations to compile your declarative language, and I'll describe one reason why you might not want to. And finally, I'll briefly illustrate this QRE-Past language. Okay, so the model begins with a set of quantitative states. So just like in finite state machines, you have a finite number of quantitative states, and here you have Q0, Q1, or Q2. And the thing that I'm adding to this model is that they're either active with a value or inactive. So I have three states. They're either active with a value or inactive, and then I have an input stream. In this case, let's imagine that I have a stream of timestamps from like an event stream of timestamps, and each message is either A or B, and then it has the timestamp has to be increasing. So here the timestamps are 6, 7, 9, and 11. And then I provide some transitions to update the states, which I'll describe what those are. But they're going to be like transitions between the states, kind of like in a finite state machine. So let's say that the computation that I want to compute is the delay between the last two A messages. So how would I compute this if I were just writing low-level code? Well, what I would do is I would keep track of the most recent A message, and then I would keep track of the difference between the last two. And that's all I need to keep track of. So similarly here, that's what we do. Q1 is going to keep track of the most recent, and Q2 is going to keep track of the difference. So what I do is Q0 you can ignore. It's just an initial state. I need an initial state. But what I do is I add transitions between the states, the quantitative states, that describe how to update the value of one state when you receive an input message. So for example, here are my two quantitative states, Q0 and Q1. What this is saying is that when I get an A message, I'm going to set Q1's value to be equal to X, where X is the timestamp of the current message. So that allows Q1 to keep track of the most recent A message. Similarly, Q2 is going to be set to X minus Q1. So Q2 is going to get the difference between the last two A messages. So Q1 will be either active with the last A message or inactive, and Q2 will either be active with the difference between the last two, or it will be inactive. And then if we read in an input stream like A, so let's say we read in A6, then Q1 would get updated with the timestamp of the message. So Q1 now is 6, and Q2 is still inactive. If I read in another message, A7, now Q1 again updates to the most recent message, and Q2 updates to the difference. If I read in a B message, everything stays the same. If I read in, finally, say, a message with timestamp 11, then Q1 keeps track of the most recent message, and Q2 keeps track of the difference. Okay, so that's basically the model. And what's going on here is that you have, well, it turns out that such a model always produces output on a regular language over the input stream. So in this case, there's A's and B's in the input stream, so the model always produces output on some regular language over AB. And what's going on is that you have these active and inactive states, and the set of states that are active forms some kind of finite control from the classical world, and the set of states that are active with a value forms kind of like a data register. So what I'm doing is I'm combining the data registers and finite control from other automata, and I'm just merging them into one model. So that's not quite the whole model. I have to tell you one other thing, and then that will end, for the most part, the technical section of the talk. But to understand the model fully, you have to understand transitions more generally. So there are two ways that transitions can be a little bit more complicated. So you can have a transition with multiple source states, which is often useful. For example, in these applications, you often want to compute something like an average, and an average is a quotient of a total and a count. So in order to do that, you need to have one state that's keeping track of the count, one state that's keeping track of the total, and then you need to divide them. So you need to have a transition like this, which sets the output to the quotient of the two inputs. And the semantics of that is just that if either of the input states are inactive, then it doesn't evaluate. So Q3 will be set to inactive unless both of them are active, and then it will be evaluated, as you can see from this table. So if both Q1 and Q2 have a value, then Q3 gets a value. And in general, this can be an arbitrary expression. The second more complicated thing that can happen is that I can have multiple transitions that both target the same state. So let's say I have a transition here and a transition here, and they're both providing a value for Q3. So what should I do? Well, if they're both inactive, or they both evaluate to inactive, then okay, I set it to inactive. If one of them is active, or the other one, then I just evaluate that transition. But the problem is where I have both transitions evaluating to some value, and I don't know which to assign to Q3. So what I do here, I mean, one approach would be to make the semantics non-deterministic, but we're really interested in deterministic applications. And we want a streaming evaluation algorithm, so we're not really interested in doing that. So what we do is we add this third state mode that I didn't tell you about before, which is a conflict. So if I get two assignments to the same state, then I just produce a conflict. And the way that conflict behaves in the semantics is as if it were a multiset of two or more values. So you can think of inactive as being 0 values, active as being 1 value, and conflict as being a multiset of 2 or more. And you can kind of define the semantics just on that. So if you divide 2 or more values by a single value, you get 2 or more values. And if you apply an operation to no values, then there's no results. Okay, so that's the whole definition. I have a finite set of quantitative states, which are in one of these three modes. They're inactive, active with a value, or conflict. I have a finite set of transitions, which are labeled with expressions to give me the value of that state in terms of other states. And then I have a set of initial states and a set of final states. Let me briefly just overview how the composition operations work. I won't go into these in detail, but I'll just show you the pictures. So here's an example of an operation from your query language or your specification language that you want to support. So maybe you have two functions, f1 and f2, and you have an input stream w, and you want to compute the maximum of the values of the two streaming functions. So you can do this kind of just like in the NFA constructions. You just put the two things side by side, and you add some epsilon transitions. And that's your implementation. So that's what your compiler does. There's a more complicated operation called split. In the interest of time, I think I'll just go over it very briefly. But the idea is you have two streaming functions, f1 and f2. And what you want to do is split the input stream into two parts such that f1 matches the first part and f2 matches the second part. So it's kind of like a more difficult operation. You have to find where is the exact point where they both match. It's non-deterministic in general, but here we can implement it similarly to NFA concatenation. So we just kind of put a copy of f1 and a copy of f2, and then apply some epsilon transitions. And then there's some more technical details to this construction, which I would point you to the paper if you're interested. OK, so let me just briefly mention expressiveness. So you can ask, what is expressiveness compared to general streaming computations? General streaming computations could be described, for example, by an initialize, an update, and an output function. And we're going to imagine that these are given by loop-free code. Well, it turns out that general streaming computations are not closed under the split function, which means they're not compositional. So you could not actually write a compiler using these general streaming compositions because you would not be able to compose them with an operation like split. But if you add a regularity restriction, which we define in the paper, then you actually can just map these to data transducers. So, and you get no blowup. So you can match exactly the complexity of general streaming computations subject to this restriction using data transducers. I'm going to skip this illustration. This is the QRE compilation theorem, basically showing that we get a guaranteed cost of evaluation. So in conclusion, we provide this model intermediate representation for general streaming computations, which supports a number of composition operations in order to support compilers for a language like QRE-Past. And it has these 4 benefits over existing models. In future work, we'd like to implement this for some target applications. And we'd also like to do query optimization using data transducers. OK, thank you.
OK, let's thank the speaker. OK, we have some questions from Slido.
OK.
It seems like a synchronous language like Lustre would be a good alternative option. Did you compare to such languages?
Right, so it is certainly very related to languages like Lustre. I would say this is a synchronous model. The short answer is that Lustre could not support these constructions like split. So we have this subtle distinction between active and inactive states, and we use this to define constructions like split. And you could not do this without kind of worrying about the active and inactive states and these the general transitions that we have in our model.
Okay, other questions?
So I'm a bit confused by these conflict transitions. So somehow, if you
by
run
the what?
conflict transitions, somehow, I mean, when you run the automatic transducer over some stream, somehow, for me, if it is deterministic, it should be in one state, and then from that state, there should be just one transition to another state, right? Why you have two conflict transitions somehow?
Right. So the reason that conflict comes up is because you can have multiple transitions targeting the state. So in general, a configuration of data transducers is a value at every state. So every state has a value, and then I may have multiple transitions giving the next value of a certain state. And that's where we introduce this conflict.
So you mean that in one step, then all the states will update their value, or?
Yeah. So in one step, you take all of the transitions together and update all of the different states.
Okay.
Yeah.
Okay. Thanks.
Yeah. Thank you.
Great. Let's thank the speaker.